We've seen a mass on a spring, and we've said, yes, this is simple harmonic motion. It goes back and forth, and it follows this expression. The restorative force is proportional to the negative displacement. So the further back you pull the spring, the greater the force towards equilibrium. And I want to try and convince you guys that this pendulum is similar. Hopefully you guys could buy that this is simple harmonic motion as the pendulum goes back and forth, back and forth, back and forth. To say for certain that it is, we need to be able to mathematically write out this for a pendulum. So that's what we're going to try and do right now. Before we do that, we're going to make a few assumptions. The cord doesn't stretch with the mass that's placed on it, and that the mass itself of the cord is negligible, and there's no air resistance. So we're trying to test out whether the restoring force is proportional to the negative displacement. The displacement here is how far back you stretch it. So to get an expression for the force, I have to draw a free body diagram. I've got tension going up, mg going down, and mg is going to be what I split up here in order to say that ft and mg cosine will balance out, and what I'm focused on here is the mg sine theta, because that's my restorative force to get this thing back to equilibrium. So mg sine theta is the restoring force, and now I have to use a bit of clever mathematics that you may not have seen before. So for small angles, less than 15 degrees, I can say that the sine of theta is about theta. You could plug a few numbers in for theta in your calculator that are less than 15 degrees, and you should get roughly the same answer. So in that case, I can say mg sine theta is about mg theta, and this helps out if I consider the definition of a radian, which is the length, the arc length that you sweep out, x, divided by the radius is, in this case L, is the angle measured in radians. Another way of putting that is L times your angle is the arc length x. So I am trying to write an expression for f and x together to see if I have simple harmonic motion. I rewrote the definition of a radian for theta. I substituted, instead of sine theta here, I just am calling this theta, and now I can substitute for an expression of f and x, which I have below. The only thing, the step here is that I put this in, put a negative sign here, because if I stretch this out to a further and further displacement x, the force is going to be in the opposite direction. So if I call this positive, that direction will be negative. So negative mgx over L is the force. And this is now in the form of F is negative kx, where k is mg over L. And this k is just based on the physical properties of the pendulum, the mass, the length, and the gravitational constant. So my next order of business is to try and write out an expression for the period of a pendulum. I'm going to try and transfer you guys over to this next whiteboard. Off we go. Can you see that? Oh yes, you guys can see that. So this was the expression that I had last time for the period of the spring. And now I'm going to use the k that I just found for the pendulum. So I plug that in, k goes on the denominator, and the m's will cancel out. So what's left is the period is 2 pi times the square root of L over g. L is the length of the pendulum. So for small angles, mass has no effect on the period of a pendulum, meaning I could keep on adding more and more mass, and I could lift this thing up and swing it, and it will have the same period. The result from last time of the spring is it doesn't matter how far away I pull this thing to an amplitude, it'll still have the same period. So for small angles, this still holds true. Whether I pull it back to 5 degrees or 10 degrees, it will have roughly the same period. And of course, I could take the inverse of this to get my frequency. Now, this has some pretty extraordinary application. One of them being the making of a clock to measure time. I could create something where the period is 1 second, figure out the length of the pendulum that I would need to create, and then figure out some ways to reduce air resistance in order to keep a pendulum going at 1 second. This is what I've done here. If you plug in all the variables that you know, plug in 1 for t, then you would get a length of about 0.25 meters. So that's what this is, and if I let this thing swing, you should be able to measure out that its period is 1 second. So that is pretty neat, I think. This also, it's interesting to think about a swing on a playground. You could put different people on the same swing, but really it will always oscillate at its natural frequency based on the length of the swing. Yeah, so that's the simple pendulum. Hope you guys understand it. I'll see you soon.